All right, on tonight's episode of Python Papi, we're back inside our artificial intelligence course, and we're still doing our neural networks module. Let's have a look at what we went over tonight. Last night, if you recall, we touched on the topic of having multiple outputs for our neural networks, and tonight we're going to pick up where we left off. So anything that we can frame as a mathematical function, something like classifying inputs into various different categories, or figuring out based on some input state what action we should take, these are all mathematical functions that we could attempt to model by taking advantage of this neural network structure, and in particular, taking advantage of this technique, gradient descent, that we can use in order to figure out what the weights should be in order to do this sort of calculation. Now, how is it that we would go about training a neural network so it can have multiple outputs instead of just one? Well, with just a single output, we can say what the value of that output should be, and then we update all of the weights that correspond to it. And when we have multiple outputs, we can really think of them as four separate neural networks, if we had four, for example. So really, we have output one connected to each of the three input neurons by three weights, for example, as its own neural network, and so on and so forth. So we have to imagine that we have three inputs and then we have four outputs. Each of those outputs will be connected to the three neurons by way of weights connected with edges, and that's going to go for every one of those neurons. So let me see if I can actually show you an example here. If I have something, let me see if I can find one down here, just so I can show you quickly what it would look like. It'll be a better explanation visually. Okay, so let's just imagine here we had four, or we're just going to call it three for now. We had three neurons, or three outputs and two inputs. So every one of these outputs will be connected to the two inputs. So we would have two connections here, two connections here, and two connections here. And each one of these outputs will be considered its own neural network because we want multiple outputs. So that's all it's saying there. Now let me go back and find my place so we can pick up with the reading. Now each output neuron will be connected to the same inputs, but all be connected by its own set of weights, like I just showed you. Each one of those outputs was connected to the inputs by its own set of weights. And so if we wanted to train a neural network that has four outputs instead of just one, in this case where the inputs are directly connected to the outputs, we could really think of this as training four independent neural networks, like I showed you. So we had the three outputs up top, and each one of those three outputs was connected to the two inputs, and each one of those outputs was considered its own neural network because it had its own edges, which had its own weights and its own connections. Now we know what the outputs for each of the four should be based on our input data, and using that data, we can begin to figure out what all of the individual weights should be. And maybe there's an additional step at the end to make sure that we turn all of the output values into a probability distribution such that we can interpret which one is better than the other or more likely than another as a category or something like that. So this then seems like it does a pretty good job of taking inputs and trying to predict what output should be. But it is important to think about the limitations of this sort of approach. Just taking some linear combination of inputs and passing it into some sort of activation function. And it turns out that when we do this in the case of binary classification, of trying to predict something like does it belong in one category or another, we can only predict things that are linear separable. Because we're taking a linear combination of inputs and using that to define some decision boundary or threshold. And what we get is a situation where if we have some linear set of data, we can predict a line that separates linearly one category of data points from another. But a single unit that is making a binary classification, otherwise known as a perceptron, can't deal with a situation that is non-linearly separable, where there is no straight line that will go straight through the data that will divide one category away from another. It's a more complex decision boundary. The decision boundary somehow needs to capture things inside of each category separately, and there isn't really a line that will allow us to deal with that. So this is the limitation of the perceptron. These units that just make these binary decisions based on their inputs. And this is the perceptron here, only capable of learning linearly separable decision boundaries. Now I'm going to leave it there for the night. We did go a lot further and we did take a lot more notes and we did do some graphing also, but we will pick it up tomorrow. And of course, I will keep you guys posted every step of the way. But for now, this is the Python Poppy. You guys stay Gucci.